Yes, I'm going to talk today about a work with my PhD student, Victor Wang, on a novel empirical risk formulation for feed-forward neural networks with non-smooth activations. So as I mentioned, this is joint work with Victor, and in case you have attended the poster sessions, you may have seen that he also sort of had a poster about the topic there. What I should mention, I'm basically doing here what I would basically normally we shouldn't be doing. I'm talking about research that's actually not yet published. That's basically still in the process of making, so there's still quite a lot to probably be reshaped in the course of while we try to finish our preprint. But so the latest state you can probably find on Victor's poster. Somewhat, but not directly related, but also since he's here and also attended the poster session, I also want to give a little sort of post advertisement for my other PhD students, poster Danilo Riccio. So please feel free, since they're all still online, please feel free to check them out. Okay, before I sort of get started, I want to give you a little outline of the talk. So I'm going to give a brief introduction of what I'm actually going to really sort of talk about today. I will spend some time on a particular sort of motivating example before I then discuss the main part of this talk, the relaxed empirical risk formulation. I will show some preliminary numerical results and conclude with conclusions and outlook. Okay, let's dive straight in. Let's start with the introduction. So what am I going to talk today about? And it's basically just training of feed-forward neural networks. So nothing really fancy there. And we have seen a lot of definitions of feed-forward neural networks today. This week, we have already seen plenty of definitions, but sort of for the sake of introducing notation, I'm going to sort of repeat this again. What I want to mention is, so I really focus today on just the training aspect and not so much on things like validation errors or other things, but just basically how can we train a neural network with a probably slightly different approach to conventional approaches. So what is a feed-forward neural network? A feed-forward neural network is basically just an iteration of the form where we have basically the application of an affine linear transformation. I'm not sure if you see my cursor, but if you can, I'm basically circling now sort of this affine linear constraint and an application of sort of nonlinear activation functions. So where we feed in some inputs, and then we have, of which we have sort of as many. So these are the number of samples. And then we feed them into this network, which has several layers. So we basically concatenate these operations here. And we say that we have L number of layers of such a network, and then generate an output by executing basically these operations in an iterative fashion. And I think I already mentioned it. So sigma here is always my notation for the activation function, whereas the matrix W here, or the operator W, is sort of denotes the weights for the particular, so layer L if it's WL, and B is the bias for layer L. And throughout this talk, I want to focus on a very particular form of activation functions, namely Proxima Maps. Sorry, I went slightly too far. No, can't really interrupt this once the animation is going. So activation functions, we want to focus on a particular class, such as, the class of Proxima Maps. So everyone who's familiar with convex optimizations has seen, probably knows what a Proxima Map is. And also we have seen a couple of examples already through other talks and other posters during this week. So Proxima Map is basically just the minimizer of this energy that is listed up here. So the squared 2 norm of the argument that we want to minimize for u minus the argument z, plus some energy psi, which in this talk is always chosen to be a proper convex and lower semi-continuous function. And to give an example, if we, for instance, have something like a characteristic function over a convex set, such as the non-negative orphaned, what we get is simply the pointwise sort of rectifier function that cuts off everything that's negative and remains everything that's non-negative. So the classical, if you want to construct a Relu, we can use this activation function and actually can also say that it is a Proxima map. So and in general, you can actually generalize an awful lot of known activation functions that are being used in practice. For instance, the soft shrinkage operator is just a multiple of the modulus for this function psi you can generate. But even if, let's say, you want to use something that is differentiable and you're very fond of, let's say, taking the hyperbolic tangent, you can actually write the hyperbolic tangent also as a Proxima map. And I think, to my knowledge, this has first been done in this citation, in this paper here by Combet and Pesquet. And obviously, there are, in this paper, but also in general, there are lots of other examples of how you can actually rewrite activation functions as Proxima maps, or derive maybe even other activation functions from other Proxima maps. So going back to the feed-forward neural network. So how is a network usually trained? I mean, we have seen this in many talks today. For instance, in one way was in the previous talk, was described in the previous talk. So, but in this general setting that we have seen in many talks this week is that we normally define a loss function that depends on all these parameters that we want to estimate. We sum up over all the samples, and we have some distance function, or sort of small loss function L, between sort of the output of the neural network, which is denoted as XIL, and the desired output. So if we're in a supervised framework, this is sort of known. Other unsupervised variants obviously also possible, where we have sort of the output of the network, but also sort of the input of the network. So this can all be written in form of this loss function. And what we have also seen this week was that often for various reasons to guarantee sort of stability or have particular sort of regular weights and not irregular weights, you normally also add some form of regularization to your parameters, like adding a regularization function, such in this case, where you act on the weights or the bias terms. What we, I think, haven't talked so much about this week, what is obviously also possible, is that you can enforce some regularization on some of the hidden layers. Let it be sort of the affine linear transformations or the outputs of the activation function. So if you, for instance, think about something like sparse autoencoders, you would impose some form of regularity on the encoding, and not necessarily only on the weights, but also on some of the layers. So we can think of this as well. So in general, it's mostly loss function plus some form of regularization that we want to minimize. And the predominant approach, or the state-of-the-art approaches for minimizing such an empirical risk, are normally gradient-based. So we have also seen in the previous talk, there are things like stochastic gradient descent with or without momentum, such as heavy ball or Nesterov momentum. There's Adam W, Adagrad, Ada delta, and obviously all kinds of other talks, you name it. They're all there, and they all have in common that they are sort of gradient-based, so they require the evaluation of gradients. And this may not necessarily be completely straightforward if, for instance, sigma is a not differentiable activation function. And sort of why is that so? To just illustrate with a simple example. So imagine we somehow end up describing or representing the identity with two sort of rectifier activation functions with different signs. Then we obviously see if we would just compute I mean, this is a differentiable function, so if we just compute the derivative, we know that the derivative should always be 1. However, if we use sort of the Clark subdifferentials for the individual sort of rectifiers and basically assume that we have some form of calculus rules on the Clark subdifferential, then we may actually end up enabling like an artificial critical point at 0 if we choose basically the same value at 0, where we have this ambiguity of choosing multiple values. So you may ask, is this actually a problem? This is like a very constructed example. Is this actually a problem in real scenarios? And I recently learned that apparently it's not necessarily a big issue for gradient-based algorithms with high probability, which sort of has been shown in this paper here in this very recent preprint by Jérôme Bold and Eduard Pauls. But we decided nevertheless, maybe can we actually find a way to not differentiate the activation functions and still train a neural network? And the second part of the motivation, although I will not really focus on it very much in terms of numerical results, is the other issue that we encounter in lots of problems, and I have mentioned things like, well, sparse autoencoders, for instance. Gradients with large Lipschitz constants often can be the bigger issue for the performance of a gradient-based algorithm, because it can slow down the performance dramatically. And just suppose we want to minimize models where, for instance, we enact really the one norm, for instance, on one of the hidden layers on some of the weights. I mean, this is a bit similar to the general sparse autoencoder field, although here we use like a one norm instead of using this KL, Kuiper-Kleibler regularization. Or another example, which I stole from the literature, is basically when you think about trying to invert neural networks. I mean, there has been lots of progress since then where people used also neural networks as regularizations, but in the early paper, in this paper here by Mahendran and Vidaldi, they decided to use a smooth version of the total variation to actually regularize the inversion of their neural networks. And something like this, even if you do smooth such non-smooth regularization functions, you normally end up with large Lipschitz constants, and that does make gradient-based training a bit more challenging. And you have to definitely use all your tools of preconditioning or normalizing your layers and whatever you have basically what tricks you have in your sleeve. So we therefore, from the perspective where I'm coming from, I mean, there's a lot of algorithms that in general seem to be potentially more suitable to handle non-smoothness, such as using proximal versions of stochastic gradient descent, but also methods such as alternating direction method of multipliers, ADMM, which we will mostly focus on in this talk, but also primal dual hybrid gradient methods, for example. Okay, so what is therefore the goal of this talk? We basically want to train a neural network without having to differentiate the activation functions, and to potentially also train them with algorithms that can also handle non-smoothness better, so that in the future we could, for instance, incorporate non-smooth regularizations fairly easily. Although I can already say that I'm not going to do this in this talk particularly, but this is definitely some of the work in progress and some of the motivations. So also before I proceed, some related literature. As I said, it's still all in the early stages, which is why the literature review is probably very incomplete, but similar research that goes into the same direction from various reasons is, for instance, a paper by Taylor and others based from the group of Tom Goldstein, already published in 2016, which proposed to use ADMM for training neural networks. Some of our own work where we interpreted sort of neural networks as iterative regularizations. Then a paper by Geiping and Möller quite recently on bilevel optimization, where we use some of their mathematical sort of tricks from there. But there's also other works by Kowalski and Stewart, for example, where they try to do derivative-free training of neural networks with a very different approach. And recently papers by Choromanska, and also a very recent publication by Goldfarb and Curtis, where they also try with an ADMM approach to train such a neural network. So we're basically in the spirit of those works, but slightly differently, as you're going to see. Okay, so that's basically to set the scene. And now I want to give you a motivating example of what we're trying to do differently for training like a neural network. And I start with the simplest neural network that we can think of, basically just a perceptron for multiple samples. But just with one layer. So we would basically normally have just a loss function, depending on sort of one weight matrix or weight operator bias. And this loss function could be anything, could be like a square 2 norm, could be cross entropy or something. We have our data samples, we have our activation function applied to the affine linear transformation, and we would like to train W and B based on this. And so the first thing that I'm going to do is I rewrite this by introducing like a constraint, by introducing basically this variable Z as I had before, to write as this affine linear transformation. And then the major difference now that we want to introduce, and everyone who knows me knows that I like to throw Bregman distances basically everything that I work on, left, right, and center. And the same is actually going to happen also here, but I have actually quite good reasons for it. So, which I'm going to show you on the next couple of slides. So we will replace this function L with a different function, so B or BI, because it will depend on sort of the individual index, where here BI is the Bregman distance. So the Bregman distance is defined here. And for those of you who do not know what the Bregman distance is, or many people call the Bregman divergence, I normally stick to distance for a particular reason, although it's not a metric. The Bregman distance is basically the distance between a function and its linearization around a particular point. So that's how you can basically always visualize it. Take a convex function, linearize it in a particular point, and take the difference in a different point. And we take this Bregman distance with respect to a particular energy, the energy basically of the sort of squared 2 norm of the argument minus sort of this variable Zi plus this energy psi. And we have subgradients here because the entire energy psi may not be differentiable. So we operate on with subdifferential calculus. For those who do not know what a subdifferential is, it's basically just the convex analogy to having a differential. So if psi is differentiable, you can just think of this as being the gradient of this energy. And so just as a reminder, so what this energy, you should probably still remember from a couple of slides ago, what is this energy? So the energy is basically chosen so that the activation function is the Proxima Map with respect to this energy. And in particular, it means it is the argument of this energy over here with respect to the argument u for like a fixed z or zi if we have multiple ones. And so this allows us to actually simplify the distance because this condition here, that sigma is the solution to this optimization problem, has an equivalent characterization, basically due to Fermat's theorem, that 0 is in the subdifferential of this energy at this argument. So it's basically the convex analogon to setting the gradient to 0. And basically, since 0 is in the subdifferential of this energy, we can basically replace this subgradient that I'm circling here with 0. So what I'm going to do down here, and therefore this Bregman distance simply simplifies. We can actually forget about this linearized term, or this inner product term, and basically just have the difference of these two energies. And this trick was basically motivated by this paper by Geiping and Möller that I mentioned earlier, although they worked with this in a very different context. So this is the energy, and you probably now wonder, okay, you have derived this weird looking energy, but why? What is it good for? So why would we choose such a distance function? It's probably the crucial question here. And the reason why I want to choose this distance function is actually the following. If we do take the derivative with respect to the argument z, or the argument zi, of this energy, what we get is basically just the difference of the activation function of the argument zi minus the argument yi, or the sample yi. That is the one thing. So if we differentiate it, we get something where we didn't have to differentiate the activation function. We basically just get the difference of the activation function minus the argument yi. And the second thing is, and that's basically a property that follows immediately from Proxima mappings is that this gradient with respect to that argument is one Lipschitz continuous, or firmly non-expansive, if you prefer. And so, yeah, basically we obtain a gradient with these two properties if we use this particular sort of distance instead. So one little explanation, it's probably the only real mathematical explanation I'm going to give throughout the entire talk, but it's actually fairly simple because it may not be completely obvious at first. But so the reason is, if you are familiar with convex optimization, is that if you put in the Proxima map into the energy E of Z, this is basically the Moreau-Yasuda regularization, for which we know that the gradient with respect to the argument Z is just basically Z minus the Proxima map of Z. So this is a well-known property known from convex optimization. And if we use this together with basically computing the gradient of this first energy with respect to sort of Y, when we plug in Y, then we just get the difference. It's basically just the gradient of this energy here. Sorry, with respect to Z, we just get Z minus Y. So if we take this energy, compute the gradient with respect to Z, we have sort of the first part, which is this here, this gradient. And then we have the second part, which comes from the Moreau-Yasuda regularization, which is this here. And so if we subtract them, we basically just end up with this activation function here minus yi. Okay, so a quick small summary of properties. Actually, it's not just a summary, it's also a couple of things that I haven't mentioned yet. So we do have this new energy B, and the distance. The caveat at first is it's not a metric in general. People normally like metrics. This is not necessarily one. However, it is actually an upper bound for the quadratics of 2 norm, basically an upper bound if we have multiple samples for the mean squared error, which I didn't show here, but it can actually be shown quite easily. We obtain a global minimum when, let's say, y really equals sigma of z. The function is actually biconvex, so it's convex in y and convex in z when the other argument is fixed. We know that the gradient, because it is basically just a Proxima map with a constant shift, is monotone. And we also know what we've seen before is that it is one Lipschitz. So these are all sort of aspects to bear in mind. And I should actually hurry up a little bit with my time. So the question is now, okay, if we replace it with this energy, so why does it add anything, and how do we actually still minimize our loss? And this is now where all these properties come into play. So there are a couple, for this perceptron example, there are a couple of different approaches. So one approach would be to just do gradient descent. And if I, for a moment, forget this additional constraint, but basically plug it into the function again, to the composition, and compute these gradients, which we have basically done before, which is just the activation function minus sort of yi with sort of the argument now, and then obviously we get like a transpose here. What we actually rediscover is basically a generalization of Rosenblatt's famous algorithm from the 50s, just with a Proxima map. So we can actually do Rosenblatt's algorithm for the perceptron training if we just have one layer. However, what I mentioned earlier is that I'd really rather like to use not just a gradient descent approach, but something where ideally we can incorporate some non-smoothness later. So another approach could therefore be to say, let's keep the constraint and do something such as ADMM, the alternating, I missed the direction bit here, the alternating direction method of multipliers, which goes back to seminal work of Gabay and Messier. So for the ADMM, what is normally being done, in case you haven't seen it, you take your objective, you add a Lagrange multiplier with your constraint, but you also add a squared 2 norm of your constraint, and then you optimize with respect to this energy alternatingly. So like a coordinate descent type approach. So you keep the other variables fixed, and then you always update one after the other. And for the Lagrange multipliers, which I didn't note here, so I take all of them, store them in matrix M, you get this gradient ascent step. So that in itself, with our formulation, doesn't really cut it, because we have this, we would have to sort of implicitly solve an optimization problem with respect to Z, which is why we go for a modification of ADMM, which has been proposed in 2014, denoted as Bregman ADMM. To be fair, there's actually quite a few Bregman ADMM versions in this paper. And we take a particular one where we add like a Bregman distance simply to linearize with respect to the argument Z. And I don't really have time to go into the details here, but if you do this, you basically just linearize your argument with respect to the variable Z here. So if we write down for our particular example, the individual steps, we get basically like an update step for W, which is just the solution of a linear system. If you don't like to solve a linear system, you can also linearize that. An update for B, you have a sort of gradient descent type step for Z. Like it looks a bit like this Perceptron Rosenblatt algorithm. And then you have this gradient descent update step. And this is now an ADMM step where you can actually train a Perceptron with basically all the normal guarantees that we always have. And I give you a small example, and I really have to hurry up because I actually want to also get to the multiple layer one. If we think about a simple one-layer Relu Perceptron example where we have an affine linear transformation and the sort of rectifier function, we use MNIST as our data set example and say we have our input data is basically just the images of MNIST, some of them stored in as column vectors of the matrix X, and then we basically do like a simple classification task, but by doing this one-hot vector encoding of Y, where basically the one always denotes in which class the image should be. And if we do train this with this ADMM approach, we do see actually that it works quite well in the sense that so I plotted here as a blue curve the norm of the linear constraint, and then here the norm of the sort of nonlinear constraint, basically satisfying that sigma of Z has to equal Y plus the Lagrange multiplier. But I also plotted sort of the squared 2 norm difference just to see that actually it does in this case also basically train the original objective. And this is just for 1,000 samples, but it goes basically, this is a log scale. So we have basically this sort of linear type of convergence behavior in this example. And it does actually, if you compare it to box standard subgradient descent, so I should also emphasize here, there's nothing stochastic because we didn't use a stochastic ADMM. So we also didn't use a stochastic subgradient descent because you can also use a stochastic ADMM version and therefore it wouldn't be a fair comparison. There's also no additional tricks. And then you get like this regular sort of slow convergence of ADMMs. There's also no momentum, of stochastic gradient descent, whereas the ADMM version converges very fast. You can obviously speed this up with tricks like the ones we've seen in the previous talk, but that wasn't really the goal here. It was just basically show that the ADMM approach works. And I did this with more samples, but where the picture is a bit different, but I'm not actually gonna talk about this too much because I'm basically already running out of time. So just a few words. So how can we now extend this to multiple layers? So first of all, this new problem formulation is obviously not necessarily the same as the original problem. So it's just an upper bound, but we can relax the original problem by introducing like an extra variable and then basically relaxing sort of this nonlinear constraint with this new function B and solve it with almost the same Bregman ADMM strategy. But the question is obviously, how do we generalize them to multiple layers? And this we sort of do by doing this for all the layers by introducing an auxiliary variable and then replacing this nonlinear constraint that this variable has to equal to the activation function of ZIL with this particular distance. And it's obviously important to emphasize that this is not the same as the original problem. That's really just a relaxed version. So we're not proposing that we can actually like train our original objective now in a magically different way. We have a different objective. Okay, very briefly, because unfortunately I'm already out of time. How do we minimize this? We can do this with a coordinate descent approach, where we first optimize with respect to the weights, the biases, and this additional variable z, and then we alternatingly always update with respect to these new x variables. We can solve both subproblems again with a Bregman ADMM approach, but we can also go for a full non-convex setting and use like a non-convex Bregman ADMM, although convergence there is a bit more of a big issue and it's not really proven yet. And then, sorry, I'm kind of skipping through this.
Martin, sorry, I'm just saying that you've got another 5 minutes, so you don't need to hurry through your results.
Oh, okay. Okay, sorry. Yeah. I thought it was because we started slightly late. Okay. Oh, that's great. Thank you. Okay, then I'll slow down again. Excellent. Okay. Also, I mean, the previous slide, if you want to see a few more details, I think Victor has some of them on his poster, but also obviously once we have a preprint ready, the details will all be in there. But just to basically now illustrate that it works is that we do have a very, it's a toy example, so it's not something sophisticated. We're really just in early stages. I show you a very simple denoising autoencoder example where we again take the MNIST data set. We have also done it with different data sets, but just for illustrative purposes, and everyone knows MNIST, I show you MNIST. So you do the most simple autoencoder that you can probably think of, other than a linear autoencoder, is by basically having a linear transformation. We have no biases here. We reduce the dimension from 784 to 64. We apply the rectifier activation function, the maximum of 0 and everything else. It's a pointwise maximum. And then we apply another linear transform as the decoder. So the entire autoencoder is basically just matrix times activation functions times matrix times data. And so the convergence behavior in this case is again with this is this Bregman ADMM algorithm. The loss values are again logarithmically scaled. The iterations are not. Sort of compared to the PyTorch versions of subgradient descent, but again not stochastic, and Adam. And at least for this simple example, without obviously any tricks again for the other algorithms like normalization layers, etc., we do actually get, with this very simplistic model, which is obviously not perfect enough to really denoise it, we do get, so we have the noisy images as input, noisy MNIST images. We know that SGD seems to not really have fully converged. It's still very blurry, whereas as Adam is already a really much better result. The proposed algorithm we have, it's obviously not a perfect reconstruction because the model is too simplistic, but it does actually seem to capture and get a lower energy, even of the energy that we don't really train it for, than the other two approaches. Okay, and with this, actually, I'd like to conclude. So what have we seen or discussed in this talk? So we basically have derived sort of an energy, and that was sort of the main purpose of this whole work, is that where we don't have to, when we compute the gradient, we do not have to differentiate the activation function. We have somehow, as a byproduct, generalized Rosenblatt's algorithm, although that's also not really what we were after. We have, and we're also not sure, maybe that generalization is already well known or also well proven. The only proofs that I knew for the Rosenblatt's algorithm, they always assume that you have this -1 +1 sort of classifier. We have introduced a relaxed empirical risk for feed-forward neural networks, although I kind of rushed a little bit over this, where we basically do this for multiple layers in this relaxed form. And we have minimized it with this Bregman modification of ADMM without having to differentiate the activation functions, and shown some preliminary numerical results, very preliminary, for this autoencoder. And there's obviously an awful lot still to do. So what I haven't done, although I kind of listed it as a motivation, we haven't studied examples with bad Lipschitz gradients, where we really, let's say, want to, for instance, sparsify the hidden layer of the autoencoder, which is definitely something that we're currently doing. We haven't looked into extending the concept to other neural networks, such as ResNets or other architectures, but I suppose as soon as you use Proxima Maps in there, it shouldn't be too difficult. And also, we haven't considered any sort of stochasticity. So obviously, in order to have a more fair comparison with many state-of-the-art algorithms, it would be good to actually look at stochastic variants. And there's probably an awful lot more that we can that we're going to investigate that I didn't put on the slide. But I want to basically leave this here. Thank you very much for your attention. Happy to take your questions. And yeah, thank you.